16.1 Propagation of a Disturbance. In this lesson, we will explore the fundamental nature of mechanical waves and the specific elements required for them to exist. We will distinguish between transverse and longitudinal pulses and look at the mathematical wave function, represented as y as a function of position x and time t. We will also examine how to represent traveling pulses mathematically and see how these concepts apply to physical phenomena like seismic waves and water waves. Mechanical waves are characterized by the transfer of energy through space without the actual transfer of matter. To create a mechanical wave, three components must be present. First, there must be a source of disturbance. Second, we need a medium that contains elements capable of being disturbed. Finally, there must be a physical mechanism that allows these elements to influence one another. A classic example is a flicked string under tension. When you flick one end, you create a disturbance in the string medium, and the tension provides the mechanism where one element of the string pulls the next one upward, allowing the energy to travel. A pulse is defined as a single bump that travels through a medium. In a transverse pulse, the elements of the medium move in a direction that is perpendicular to the direction in which the wave itself is traveling. Looking at the illustration of a hand moving a string, the hand acts as the source and the string serves as the medium. As the hand moves up and down, the pulse moves horizontally. It is important to note that the shape of this pulse, also called the waveform, typically changes very little as it travels along the medium. To better understand transverse motion, let us look at a specific point on the string labeled P. As the pulse moves to the right, point P does not move to the right with it. Instead, point P moves vertically up to the crest of the pulse and then moves back down to its original equilibrium position once the pulse has passed. This confirms that no part of the string actually moves in the direction of the wave propagation. Only the disturbance and the energy move forward while the medium itself oscillates locally. In contrast to transverse waves, a traveling pulse is considered longitudinal if the elements of the medium move parallel to the direction of the wave's propagation. A great way to visualize this is with a stretched spring or a slinky. If you quickly push and pull one end of the spring along its length, you create a compressed region. This compression travels down the spring. In this case, the coils of the spring move back and forth horizontally, which is the same direction that the pulse is traveling. Some waves in nature are more complex and exhibit both transverse and longitudinal components. Ocean waves are a primary example. When a wave travels on the surface of deep water, the individual water elements move in nearly circular paths. This means they are moving both up and down and back and forth. We use specific terms to describe the vertical positions. The crest is the highest point of displacement, while the trough is the lowest point of displacement. The red arrow in the diagram indicates the overall velocity of propagation as the wave moves across the surface. Earthquakes generate seismic waves that travel through the Earth in three dimensions. There are two main types. P waves, or primary waves, are longitudinal waves. They are the fastest, traveling at 7 to 8 kilometers per second, so they arrive at seismograph stations first. S waves, or secondary waves, are transverse waves and travel more slowly at 4 to 5 kilometers per second. By measuring the time difference between the arrival of the fast P waves and the slower S waves at 3 or more different stations, geologists can triangulate the exact location of the earthquake's epicenter. Mathematically, we use a wave function, y, as a function of x and t to represent the position of a medium element. The variable y represents the transverse position, x is the location along the medium, and t is the time. At time 0, the shape of the pulse is described by some function f of x. If the pulse moves to the right at a constant speed, v, its shape at any later time, t, is given by the function f of the quantity x minus v times t. Conversely, if the pulse is traveling to the left, the wave function is expressed as f of the quantity x plus v times t. Let us look at a numerical example of a pulse moving to the right at a speed of 3 centimeters per second. The wave function is given as y as a function of x, and t equals 2 divided by the quantity x minus 3.0 times t squared plus 1. At time 0, the function simplifies to 2 divided by the quantity x squared plus 1, with the peak centered at x equals 0. After 1 second, the pulse has moved 3 centimeters to the right, and after 2 seconds, it has moved 6 centimeters. The maximum height of 2 centimeters always occurs when the term x minus 3.0 times t equals 0. To summarize, mechanical waves require a source, a medium, and a physical connection between the medium's elements. They are a means of transferring energy without the transfer of matter. We classify waves as transverse if the medium displacement is perpendicular to the propagation, and longitudinal if the displacement is parallel. Finally, we can use the wave function y as a function of x, and t equals f of the quantity x plus or minus v times t to describe a pulse that maintains its shape while traveling at a constant speed. To check your understanding, consider a stadium wave where fans stand up and sit down as a pulse moves around the stands. Is this wave longitudinal or transverse? Think about the direction the fans move compared to the direction the pulse travels. Also, look at the wave function y as a function of x, and t equals f of the quantity x plus v times t. Based on our mathematical rules, which direction is this pulse moving? Finally, if we wanted to represent a pulse that was exactly twice as high, how would you change the mathematical expression?